Howdy class. Today we're going to go over tangent lines and we'll see later on how tangent lines relate to limits, and we'll see even later on how these two concepts will come together to form a very central idea of this course, the derivative. So we want to make sure that we understand both tangents and limits very well, and we'll be spending a few weeks on both of these subjects before really getting into the derivative. But you really do want to pay attention to this subject material. And we're going to start off with a geometric understanding of the subjects at hand. And this geometric understanding is going to be very helpful as we move through the subject. So let's go ahead and take a look at this right here. A tangent line is a straight line that touches a curve at a point and goes in the same direction of the curve at that point. So picture-wise, what does that look like? Well, let's say we've got a curve that looks like this. A tangent line would be any line that touches the curve. It doesn't matter what the point is, so let's make it a random point. And it's going to go in the same direction of the curve at that point. So if you had a tangent line at this point, it would look like this. And of course right here where it's kind of straight, it's going to very much follow that line right there. And so that's what makes a tangent line, right? It touches the curve at a point and then it goes in the same direction. Alright, so here is a little interactive demonstration I've set up for you guys. You notice that we've got this curve here that's in red, and then we've got the tangent line that's in blue. And note that the tangent line is touching our curve at a single point, or right here, and it is going in the same direction of the curve at that point. So, and you notice it does hit the curve over here. That's not a problem. The direction of the curve is defined by this point right here. And as you can see, as we move along from the left to the right of the curve, it just follows that path. And you can see as we get closer up in here, the curve starts to look more and more in line with this curve right here. And if I can kind of take off or ease that restriction there, so let's go a little bit further on. And you can see that it'll starts looking very close to that curve as we get closer to it. So, alright, so that is a tangent line. And so now let's go ahead and talk about a secant line. And a secant line is also a straight line, just like the tangent line was, but there's going to be a difference here. A secant line is a straight line that intersects a curve at 2 points, right? Whereas before the curve was the direction the curve went was defined by 1 point. Now it's going to be defined by 2. All right, and so what does this look like? Well, let's say we've got our curve going right here, and then we've got a point here, and a point right here, and then and right here, it keeps deleting on me. And then we got our second point here. What's that straight line going to look like? Well, you just connect the 2 points, and there's your straight line. And so that would be our secant line. And what we're going to find is as you bring this second point closer, if you brought it to where the second point was close to here, you begin noticing that the secant line can be used to approximate a tangent line. And this is going to be very important moving into the future. So what we're going to say is these 2 points are close together. If they're close together, then the secant line resembles a tangent line. Okay, it will never exactly be a tangent line depending on the curve. If the curve you're trying to draw a tangent line is itself straight, then that would be the one case where the secant and tangent line can be the same. But in general, they're not. It's never going to be straight. It'll be some kind of curvy linear line that you're looking at, and so you'll never be exactly on the money, but you'll be close enough for any purpose. So let's take a look at this on the graph. Alright, so here we've got a graph of our tangent line as we did before in blue, and then our curve, once again, that's in red. Now we've got another line. This is our secant line, and you notice that this curve is defined by 2 points. The point right here, and then the point right here. And as you move this closer in, what happens to our secant line? Well, you can see it's starting to look an awful lot like our tangent line. And when you get to this point, it starts to look like they could be identical. But when you zoom in, you gotta zoom in real close, so they look pretty identical here. There we go. So you gotta zoom in real close to kind of see the differences, but you can clearly see that there is a little daylight in between the tangent line and the secant line. So for any curve that is curvilinear, i.e. not straight, that means that there will always that your secant line can approximate the tangent line, but will never be exactly identical to a tangent line. Okay, so now for this, back to the handout, we're going to go ahead and come down here. So now we're going to go ahead and take another look at the graph, or at the handout here. We've got another graph, a little bit different than before, but very similar. This time we're going to get some of our, actually write it down ourselves. We want to make sure that we're writing this on our own sheets of paper. Reminder, if you have not printed this handout already, make sure you do so. You really want to make sure you're writing along with me on this lecture. There's really no better way to make sure that you learn this than to write everything down with your own hand. Okay, so let's take a look at this. With a different color pencil, draw a tangent line approximate to the curve at the point 3, 1. And so we have 3, 1 right here in that dot, so we want to draw a tangent line as close as we can. Okay, that one looks really good. Again, just sketching, it doesn't have to be right on the money. Alright, and what we want to do is we want to just approximate the curve of the slope. Again, it's not going to be perfect, but we want to, do our best and get close. We'll go ahead and zoom in a little bit here. Okay, and we can see that we hit this point right here. When I eyeball that, let's see, looks like that's a little bit more than halfway of the halfway. Let's go ahead and call that at 3.75. Again, we're just making an approximate. It does not need to be directly on the money. Okay, and so note that we're coming down a distance of 1. Right, going 1, and then we run over a distance 0.75. All right, so we want to calculate our slope here up on the side, and so slope is rise over run, and so our slope is about, so I'm just putting approximately equal because it's not a definite on the money, because we're just kind of eyeballing it. And so rise over run. In this case, we didn't actually rise. We went down. We went down by a distance of -1. And then for the run, we ran over 0.75. Okay. And let's go ahead and get this as a rational number. So -1 over 3 divided by 4. Which gives us a slope of -4 over 3. Alright, so that's the slope of our tangent line. Let's go ahead and put that subtan, TAN for tangent. Alright, so for part A, draw a secant line for the following points and calculate the slope of the secant line. Alright, so we've got the first one. Note that these are all based off the first point, 3, 1. And so for this first one, we're going to start at 3, 1 and 6, 4. Alright, so let's go ahead and look at the point 6, 4. That is right up here. And note that if you draw a secant line between those two, it looks something like this. And note that this secant line looks nothing like that tangent line. And that's, by virtue of them being so far apart that you really, capture all the shenanigans that are going on in this circular region here. So let's go ahead and just calculate our secant line. Just kind of see how this works. So the slope of the secant line equals 4 minus 1 over 6 minus 3. 4 minus 1, that gets us 3. 6 minus 3, that is 3. And so we have a slope of positive 1. So we note that this slope is very different than the slope of the tangent line that we have approximated. So let's go ahead and look at the next point right here. 3, 1, and 5, 1. So we plop our second point right here, 5, 1. And then we draw our secant line between these two. Okay, that's a straight horizontal line. That should be visually obvious as well as when you look at the coordinates. And so it's going to have a slope of 0. And so when we calculate this slope, all right, we're doing, again, rise over run, because that's our slope. We end up with 1 minus 1 over 5 minus 3. Well, that's going to be 0 divided by 2, which is, of course, just 0. And as a reminder, as a urgently needs heating reminder, should I say, you can divide a number into 0. You simply cannot divide anything by 0, right? 0 divided by 2 is fine, but if I said, what is 2 divided by 0? 2 divided by 0 is undefined, right? If you have a 2 divided by 0, if 0 is ever in the bottom for anything, note that that is going to be a number that is undefined. And that's going to be a very important part of this course. So make sure you know that. Just always keep in mind, you cannot divide by 0. And a lot of parts of this course are going to be ways to try and get around that fact. But just remember, no dividing by 0, not now, not ever, not under any circumstances. Okay, so the next one, 3, 1, 4, 0. So 4, 0, that point is right there. And let's go ahead and draw our tangent line. Like so. You can see, it's not quite on the money, but it's definitely getting a lot closer. And so let's go ahead and calculate the slope of this particular secant line. So we have here 0 minus 1 over 4 minus 3. Again, just rise over run. And so we have a negative 1 over positive 1. That's a slope of negative 1. So you note that we started off with a slope of 1, and then 0, and then negative 1. And you can see that as you start getting the second point closer and closer, we're going to start getting really close into the actual point, because negative 1 is a lot closer to negative 4 over 3. We just need to go another negative 1/3 over on the slope, and then we will be where we need to be. Okay, so on the A, B, and C, you notice we started off on the right, and then we started working our way in like this. For D, E, and F, we're going to start over here at 1, 3 as our first point, and it's going to start working its way closer and closer in. So let's go ahead and do one. I'll go ahead and use this light blue as for our secant line, so you can kind of see the difference a little bit easier. So you can see already we're starting off visually much closer than we did before. And so when we calculate the slope of this guy, we have 3 minus 1 over 1 minus 3. And so this will become positive 2 on the top. And then the bottom, we're going to have a negative 2 down there, giving us a slope of negative 1. So we're already a lot closer. We're actually pretty much where we were over here. And so let's go on to the next point at E. We are at 2 and 2.5 as our point. So 2 and 2.5, that's going to be right there. And then let's go ahead and draw our secant line, which will be from here to there. So it's already looking pretty good so far. So go ahead and calculate that slope. So we have 2.5 minus 1 over 2 minus 3. Go ahead and run the numbers in this one, and you will get 1.5 divided by negative 1, which of course is just negative 1.5. Okay. And to put this in terms of a rational number, this is negative 3 over 2. So just negative 1.5. So that's already pretty close to negative 4/3. Again, that's negative 1 1/3 if you want to look at it in terms of a mixed number. So this next one, 2.5, 1.75 is the next number here. So you come here, you get pretty close. All right. So we had this going here, and then we had another point going here. It's getting kind of messy in there. So let's go ahead and just look at the numbers over here. I think you guys are kind of getting the idea by now what's going on with that graph. And so when you calculate the slope of the secant line, you get the following. We get 1.75 minus 3, all divided by 2.5 minus, sorry, that should be 1.75 minus 1 over 2.5 minus 3. And so when we calculate this through, we get 0.75 divided by 0.5. And this is the same as 3/4 divided by 1/2, which we can rewrite as, let's get the negative, sorry. And this further reduces to negative 3/2. Okay, and so you can kind of see how, the closer the points, the two secant points get to each other, the more and more it resembles a tangent line. That is the point of this exercise. And so let's go ahead and move on. We got a little note here. Note that the slopes of the secant lines get closer to the slope of the tangent line as both points get closer to each other. Okay. All right, so now we're going to look at a physical example. By physical example, I mean, we're tracking an object with this graph here. This is a space-time graph of sorts. We've got time on the x-axis, and then we've got one spatial dimension graphed right here. In this case, this spatial dimension being graphed is simply up and down as in distance from the Earth's surface. Okay, so let's go ahead and take a look at this. We want to find the slopes of the secant line between 0 and 4 seconds. So 0 seconds is here, 4 seconds is here. And then you look at the tangent line in between, the secant line in between those two. Straight line there. Pretty easy to see that the slope is 0. So our slope here is 0. And again, SEC stands for the slope of the secant line. Okay. All right, part B. Between 0 and 2 seconds. All right, there's our secant line there. Obviously, it's going to have a positive slope, so let's go ahead and take a look at it. So the slope of the secant line for part B And we start off at 0, 0, so that makes things a little bit easier. So rise over run. It rose up 3 meters, and it ran over 2 seconds. And so let's go ahead and turn this into a decimal approximate this time, and this is going to be 1.5 meters per second. Okay, now for part C, between 0 and 0.25 seconds. So 0.25, that's about here, so it's going to be close to there. Note visually how we're getting closer and closer to the tangent line, at 0. As a matter of fact, it's hard to tell any daylight in between these 2 points, between the secant line and the curve itself. And so that's a good sign that we're getting a good approximation of the tangent line. And so our slope this time is going to be, all right, so we rose up, looks like it's about 0.75. So we rose up about 0.75 meters, ran over 0.25 seconds. So we want to get this onto a decimal approximate. So we've got 3 over 4 divided by 1 over 4, and again that's meters per second. All right, so we can see the 1/4 cancel on the top and bottom, and so the slope is about 3 meters per second. All right, so now as to the discussion question here, what is the physical meaning of these slopes? Well, we have, distance per time. What is distance per time? That is a speed. So the physical meaning of these slopes is that we are dealing with speed, right? It is a rate of change. How many meters do you cross in a given second? All right, so we're going to go ahead and close this off by developing a formula to help us determine the slope of a secant line. Okay, and the point of this is to kind of show you where some of these formulas come from. And we're going to do that by just developing it on our own. So first, we're here. We want to mark an arbitrary point on the x-axis and call it A. So we'll mark this point here, right? And we're going to go ahead and call that A. And now we want to mark a second point and call it A plus H. So we'll put it about over here. A plus H. So note that what happened, we started off at a distance A, and then we moved over to here, and that was a distance H, right? The distance in between those 2 points is H. So we have point A on the x-axis and then point A plus H. So that's going to go up there. All right. On the curve, mark the coordinates A, f of A, and A plus H, f of A plus H. So here, this is the coordinate here, A, comma, f of A. All right, those are our x and y coordinates. And then over here, this point, that is, the x-coordinate is A plus H, and then the y-coordinate is f of A plus H, right? Where that f is the function governing the graph. All right, so on the y-axis, we want to mark f of A and f of A plus H in their proper response, right? So this is clearly f of A right here. And so we want to mark that, f of A. And then this point right here, that's about, right there. And so that is f of A plus H. All right. So here's where we want to start calculating the slope of the secant. All right, so we want to figure out, okay, what is the change in y in between those 2 points? right there. And so that's just going to be the second point minus the first point, right? And that is our change in y. And then, of course, our change in x is our h. Alright, so now let's go ahead and put all this information together. We want to calculate the general slope of a secant line for a given function. Right, and so the slope of a secant line, right, that's just the change in y over change in x, right, between the 2 points. And so this becomes change in y over change in x. What is change in y? Well, that is f of a plus h minus f of a divided by our change in x, which was simply h. All right? And this is a formula we're going to use to calculate the slope of the secant line in general. It's a very important formula. This formula is not going to be forgotten in a week. It will not be forgotten in 2 weeks. It will not be forgotten by the end of the first exam, or the second exam, or the third exam. This formula, if you're taking Cal 2, will be used in Calculus 2 as well, in Cal 3, and probably every single math course you take from this point moving forward, you will see this guy in some shape or form. So pay attention to this formula here. It is very, very important. Okay, so having said all that, there's another question on there. Ask yourself, what would happen if h becomes very small? Right? So if h becomes very small, what happens? Well, this second point here begins to move in towards the a, right? So if the point becomes sufficiently small, right, there's not much difference between a and h, and so this point over here will be sliding along with it, right? And so we get right into right there. So what happens when h is very small? I'll tell you what happens when h is very small. The slope of the secant line formula that we have will start to come very close to the slope of the tangent line. And this is the second point that is very important, and you need to make sure you do not forget it. Okay, so after this we're going to be plotting the function y equals 5 times cosine of x into a program called Desmos. And we want to have a secant line that is a good approximation of the tangent line that is passing through. And I've got 0, 1 that should say 0, 5. There we go. And so I'm going to go ahead and change that there. And so also note that if I ask you what is f of 0, well, f of 0 is going to be 5. All right, so that's kind of important because what is the cosine of 0? Cosine of 0 is 1. 5 times 1 is 5. All right, so we want a secant line that is a good approximation of the tangent line. It's going to pass through 0, 5, and then we've got to have a second point. We want the second point to be close to 0, 5 in order to approximate a tangent line. And then we're going to proceed to zoom in until we get until the line appears to be a straight line, right, with the curve. So let's go ahead and take a look at what we have here. Okay, so note that we've got the graph f of x equals 5 times cosine x. And then I got a bunch of other things programmed into here. Again, note that f of 0 is 5, and so but instead of putting it that way, I have f of 0 plus h. I could easily come to this point here. Instead of writing 5, I could have wrote f of 0, and it doesn't change anything because, again, f of 0 is the same thing as 5 in this very specific case for this equation. All right, so based on this, just kind of like looking, it appears to be in line with the graph. But when we look a little bit closer, right, you start to notice, there's a little bit of daylight in between our curve and our function, right? It's our graph is a little bit off. We need to bring this second point closer in. Until we get to there, that looks pretty close. Not a whole lot of daylight here, but let's zoom in a little bit close. We can still kind of see, the graph is cutting off down on the sides here, and so we start zooming in. Our graph is starting to look really straight. But note that when we zoom into this scale, this resolution, if you will, you can see that there's still a little bit of daylight in between the graph and our secant line. So let's go ahead and bring this closer in. Okay, yeah, it's looking pretty close. Close enough for this resolution. You can see that the graph doesn't look, the curve itself doesn't look straight, but that's okay because we're interested in the secant line right now. Let's go ahead and zoom in. Everything appears to be good. And I kind of want, at this scale, I want you to take notice of something. Hold on. Here it is. Take notice of something. Let me go ahead and turn the secant line off for a second. Note that when we zoom in this close, it's kind of hard to see that this is in fact a curved line. It's starting to look a whole lot like a straight line, right? This is our curve. But when you zoom in super close, the curve begins to look a lot like a straight line. And so this is going to be true of any smooth curves. Any smooth curve, if you zoom in close enough, where you have the scale at 1 to 1, will appear to be a straight line. Okay, it's all a matter of how closely you zoom in. But it's important to note, even at that close zoom, it's not truly a straight line, but you're getting closer and closer to approximating that straight line. So that approximation is a lot about what this course is going to be about. So let's go ahead and bring our secant line back on. Let's go ahead and zoom back in there. You can see that there is, in fact, a little bit of daylight between the secant line and our line, but if we bring it in even closer, those appear to be perfectly in line now. But what happens if we zoom in more? I'm sure you guys are already guessing. You zoom in close enough and you will see a little bit of distance in between those 2 points. So you got to get to a point where, is it good enough? And I would say here, for almost any purpose, this would definitely be a good enough approximation, although there are situations where that would not be the case. So just keep in mind, everything appears straight when you zoom in close enough, but there will always be a little bit of variance. And this will be partly what we explore, or a big part of what we explore for the remainder of the semester. I hope this has been very informative for you guys. And until next time, I will talk to you then.